Hey everyone, this video is a part of a video lesson series that I'm using in my AP Calculus AB class. I'm putting it online for anyone though, in case it would be helpful. This is the third section in the unit that we are studying on limits and continuity. And I have to be honest with you, I'm really surprised that I'm only on the third section at this point. When I thought about it though, I realized that's because the first section took me 3 videos to get through because it's a really long section. The second section, I was determined to only get the lesson done in 1 video. However, when I was done recording, I realized that the video wasn't an hour long. Yeah, I talked about infinite limits for a whole hour, and I didn't even realize it. It's a problem I have. I can't stop when I get going. So for this video, my goal is to definitely teach you the definition of continuity at a point, talk about types of discontinuities, and the intermediate value theorem. That's what we'll be discussing in this video. But a secondary goal of mine is to only make 1 video for this section and keep it under an hour long. I don't know. I'm not making any promises that it's actually going to happen, but let's see. Okay, here we go. All right, I don't want to waste any more time. So prior to taking calculus, you have, I'm sure, heard of continuity and points of discontinuity. And you may have seen a definition like this one. A function is continuous if you can draw it in one motion without picking up your pencil. And so what you're looking at here is just a little curve on an interval from A to B, and we would say that that curve is continuous everywhere. However, what you're going to see now that you know limits is a better definition of continuity. In particular, in AP Calculus, we talk about continuity at a point and always making sure to establish continuity at a point when we're applying things like derivatives and integrals and those sorts of things that you'll see much later on in the class. Okay, so I put 2 definitions here. The one that you're seeing in blue is very straightforward and simplified. A function is continuous at a point if the limit is the same as the value of the function. The other definition that I have here, it breaks it down a little bit more and it's more specific. It's saying the same thing, it just is showing all of the pieces to it. A function is continuous at a point x equals c if the following 3 conditions are met. 1, f of c, we would call that the function value at x equals c, is defined, meaning that the point has a y coordinate. 2, the limit as x approaches c of f of x exists. That means that the left-hand limit as x approaches c and the right-hand limit as x approaches c are the same. They both exist. They are the same, and they're real numbers. And finally, number 3, the limit as x approaches c of f of x equals f of c. The statement that you see here in blue is basically saying this, and this is the most important piece. Okay, I'm going to try to use my pen here today. Let's see how this works. Ooh, I have something fun to show you in a minute. Okay, but here, this is the most important thing that you need to take out of the definition for continuity at a point. If you can establish this equation, then you can say that your function is continuous at x equals c. So the first example that you see in this set of notes, I forgot to mention in my opening, as usual, I always have a printable set of notes that go along with these lessons, and you can find a link to the set of notes in the description of this video in case you would like to access them to use to go along with the video. All right. So what you're seeing in this first example is just a simple little graph that is over the interval from x equals 0 to x equals 4. And it has 2 points of discontinuity. I think you can pretty clearly see them. They are at x equals 1 and x equals 2. And I like to start with something simple like this where you can very easily see the points of discontinuity so that we can show how the definition of continuity at a point fails for those points. And then what we do is we take away the graph and we start to look at like the structure of a function to talk about discontinuities. All right, but again, let's start with something really easy. Let's look at x equals 1. Okay. so I'm just going to write here for x equals 1. Oh no, I changed color, and you know what happened. If you watch any of my other videos, you know that this is like such a peeve of mine. I can't stand it. Smart board, can you fix that for me? How do I fix that? Okay, sorry. So for x equals 1, what's going on here is that we do have the function value existing. It's right here. However, we don't have the limit as x approaches 1 existing. And so that's what I'm going to focus on. I'm going to say that the limit as x approaches 1 from the left, this is not defined. Let's just call it y equals f of x. Not defined very clearly here. We'll call it f of x. The limit as x approaches 1 from the left of f of x, look at what's happening there. So approach x equals 1, but stay on the left, and you're going toward a y value of 0. Okay, however, the limit as x approaches 1 from the right of f of x is equal to what? Okay, so approach x equals 1 from the right, but stay to the right of x equals 1. What's the y coordinate you're at? And that's, oh, that looks weird. That's 1. Sorry, my equal sign looked weird. And so the left and the right hand limit do not match, and so therefore we would say that the limit as x approaches 1 of f of x does not exist, and that is your reason for there being a discontinuity at x equals 1. Next, let's look at x equals 2. Okay. For x equals 2, we have a function value existing, and this time I am going to note it. And I would note it like this. F of 2 is equal to, where's the y coordinate of that closed point? What is the y coordinate of that closed point? It's 2. So this is called the function value. You always look for where the closed point is to identify the function value. If there is no closed point, that's when you say that the function value doesn't exist. Okay, however, what we can see here, and I don't think we need to spend time breaking this one up into left and right because it's pretty clear that both from the left of x equals 2 and from the right of x equals 2, you are approaching the same y coordinate, and that is 1. So I'm just going to write that as a limit as x approaches 2 of f of x equals 1. So we have our function value existing. We have the limit existing. However, they don't match. So I would finish by saying f of 2 does not equal the limit as x approaches 2 of f of x. And that's our reasoning for why there is a discontinuity at x equals 2. Okay, so this opening exercise was just to show you how you can apply the definition of continuity to point to show that it fails for a couple different types of discontinuities. And let's talk about those different types of discontinuities now. I think that's a good time for that. So whenever you have a situation like this one, where I'm looking at the x equals 2 situation here, where the function value exists, it's a real number, the limit exists, it's a real number, however, they do not match. That is called a removable discontinuity. We actually say that we could redefine the function to remove that discontinuity very easily, and that is because the limit exists. And so you see two different types of removable discontinuities here. You see one where there is no function value, the limit exists, however, the function value does not exist. And this is an example where both the function value exists and the limit exists, however, they do not match. And so we would say that that's still a discontinuity there. So the key thing to take from what we've discussed so far is that for removable discontinuity, let's just say that all of our discontinuities are still let's just call them x equals c. Okay, just to have a variable to use there. What we would say is, and let's call our functions f of x. The limit as x approaches c of f of x exists. However, okay, did it stop? Sorry, technical difficulty. I've gotten real good at pausing the video, though, when things start to go really wrong. Okay, so I finished my statement here while I was paused. Characteristic of a removable discontinuity is the limit as x approaches c of f of x exists. So you have a limit. However, the limit value does not match the function value, and that is how you can show that you have a removable discontinuity. Non-removable discontinuities, there's two in particular that we're going to focus on. That would be a jump discontinuity or an infinite discontinuity. Now, if you're using my notes packet, you would see that I also put here, maybe I shouldn't put it right there. I'll put it up here. I put in the notes that we also many times call this a vertical asymptote. That's actually much more common. However, you can classify it as an infinite discontinuity. And if you remember from the last section, that's because when you approach a vertical asymptote, it is always, the limit is going toward infinity or negative infinity. And so that's why we call it an infinite discontinuity. These are the two that we're going to focus on for our other examples today. We won't be talking so much about oscillating discontinuities. I will give you one example of a function that is an oscillating discontinuity or has an oscillating discontinuity. Something like y equals sine of 1 over x, that would be an example of a function with an oscillating discontinuity. Okay, but that's about all I'm going to say about that, is that they're out there. Let's talk a little bit more right now about jump discontinuities and infinite discontinuities and the how they fit with the definition of continuity at a point failing for these types of discontinuities. So for a jump discontinuity, how you establish that it is a jump, we already saw one of those. Remember right here, x equals 1. This is a jump, right? You can say that your limit as x approaches that value does not exist. I guess a little bit more to that, though, is that you do have, so the limit as x approaches c of f of x from the left exists, meaning it's a real number, or the limit as x approaches c from the right of f of x exists. However, they don't match, or you could just say the limit as x approaches c of the function does not exist. Okay, can you read all that writing? I hope. Shoot me a question if you can't read that. Okay, so that's characteristic of a jump discontinuity. Finally, for an infinite discontinuity, this is like looking at our definition of vertical asymptote that we saw in the last section. You would say that the limit as x approaches that value of your function is either equal to positive or negative infinity. And that's how you show that you have a vertical asymptote or an infinite discontinuity. So let's take that information and let's apply it to some examples where we're not just looking at a nice graph that just clearly shows where our discontinuities are. We're going to have to dig a little bit deeper into an equation of a function to see where the discontinuities are and then what types they are. Okay, so in example 2, we are looking at a function and we're asked to identify the discontinuities. Where are they? And then we're going to use limits to classify what types of discontinuities they are. Our function here is f of x equals x cubed minus 1 over x squared minus 1. So if you're looking at an equation, what you want to think about to find the discontinuities is where are the restrictions on x? Okay, what can x not equal? And so the first thing that I'm going to do is factor the denominator. Let's just leave that numerator alone for a moment. We will eventually factor it. But factoring the denominator just easily answers this first part for us. What is x not allowed to equal? These would be called our restrictions. We would say x cannot equal -1 and x cannot equal 1. So that's where our discontinuities are. Okay, but now let's do a little bit more. Let's talk about what's happening at each of these. What's happening at x equals -1. Let's see what's happening at x equals 1. And I actually think I'd like to do the x equals 1 point first, just because we've already seen one like that today. So how do I know, what's going on here, what type of discontinuity I have? Well, I could do a little bit more with our equation. Namely, I could, and I'm going to put this up here, I could factor the numerator. Oh, and this is where I can show you my cool thing, if it works. It was working earlier. Okay, can I move it? Yes. Okay. So I'm going to factor the numerator. I see a difference of cubes there, and so I could use my difference of cubes formula to factor that, or SOAP if you know it like that. X cubed minus 1. I'm trying to be good at this, okay? I'm sorry, I'm being slow. I know, the clock is ticking. X cubed minus 1 factors into x minus 1 and x squared plus x plus 1. There you go, with the 1 there. And then I already have my denominator factored, x minus 1 and x plus 1. It worked. Okay. I was so nervous. Okay, I don't know how much I'm actually going to use this because, it kind of takes a while, but here it is. And that's kind of cool, right? It's better than looking at my writing, my handwriting on here. I just realized that this thing existed up here, so I was like, let's see what happens, and I like it. All right, anyway, now that we have the numerator and denominator factored, we can actually really easily figure out the types of discontinuities that we have at x equals -1 and x equals 1. But again, I want to take a moment and talk to you about it in terms of limits, just so we understand in terms of limits what's happening here. So again, I'm going to look at x equals 1 first. What's happening there? Well, what I see is that the x minus 1s, there's a factor of x minus 1 in the numerator and a factor of x minus 1 in the denominator, right? So they can divide out, they can cancel. And so I can say when I take my limit as x approaches 1 of f of x, I could use a simplified form where these cancel, and I'm just looking at the x squared plus x plus 1 over x plus 1 that remains. And so what I want you to see here is that we can get an answer to this limit. It's a real number. What's it going to be? 1 squared plus 1 plus 1, 1 plus 1 plus 1 over 1 plus 1. 3/2 is our limit. And since we can do that, since we can redefine the function by removing the factors of x minus 1 from the numerator and denominator, and then use that to redefine function to find a limit value, that means that what you are looking at here is a removable discontinuity at x equals 1. Removable. I guess I should put the word discontinuity in there. Isn't that beautiful? All right. And so just so you know, another word for removable discontinuity is just like simply a hole. And if you were to look at the graph of this original function, x cubed minus 1 over x squared minus 1, you would have a hole at the point 1, 3/2. Okay. All right, now for the x equals -1. Take a look at our rewritten form here. We were able to cancel the factor of x minus 1 from the denominator. However, we are not able to cancel the factor of x plus 1. This quadratic x squared plus x plus 1, it does not factor any further. So that's stuck there. And really, that tells you all you need to know. That tells you that you have a vertical asymptote happening at x equals -1, or you could call that an infinite discontinuity. But the way that we're going to write this is like this. We will say that the limit as x approaches -1 from the left of f of x is equal to something, and because I already told you that it is a vertical asymptote, you should know that it's either going to be plus or minus infinity, or either going to be negative or positive infinity, I should say. Okay, and then the right-hand limit will be the same. Okay, I'm back again. I paused the video because I was having technical difficulties, but also I realized that when I had it paused that this would be a really good time to set up my graphing calculator before I continue with this example to save time again. All right, so what we were looking at here is what's happening with our limit as x approaches -1 from the left and the limit as x approaches -1 from the right. So you could use some numerical reasoning to figure that out, or you could, okay, just to save us a little bit of time, I want to just look at the graph of x cubed minus 1 over x squared minus 1. And what you can see is that at x equals -1, there's a vertical asymptote, right? And what's happening to the left of x equals -1 is that it is going to negative infinity. And just to bring that graph back up here one more time, you know what, I'm going to do this because I actually want to do one other thing with the graph. I'm going to screenshot it and just paste it right in here. Okay, here it is. And the limit as x approaches -1 from the right is equal to, look at that, it's going up to infinity. And so therefore what we have here is an infinite discontinuity at, that says discontinuity, trust me, at x equals -1. All right, finally, the reason I screenshotted this was because I wanted to show you something that's kind of deceiving on your calculator. The calculator graph only looks like there's one point of discontinuity, right, at x equals -1. You know, though, that there is also a discontinuity at x equals 1. The calculator just does not do a good job of showing that to you on the graph. So what we should have right here, if you were to sketch this graph for yourself, is you should be putting a hole at the point 1, 1.5, because that was the limit value, 3/2, 1.5. I do want to show you, however, that if you look at the table, you do see that there are two places where there is an error in the y column, and so that would indicate that there is a discontinuity both at x equals -1 and x equals 1. All right. I really like that problem, by the way. So that's just sort of, again, applying your definition of continuity at a point to show where the discontinuities of a function are. And in the you try section, I'm going to leave A for you to try that for yourself. If you're a part of my classroom, I will be asking you about that one in a little form or a little question on Google Classroom. But I would like you to try that one. It's really similar to what we just did in the example 2. Okay, I in this you try section, though, I do want to go over part B with you because that's a piecewise defined function. We haven't seen one like that yet in this form. So h of x is equal to piecewise defined function defined by x squared minus 1 for all x less than -1, and then it changes to the function 4x minus 4 for all x greater than or equal to -1. Whenever you're looking at a piecewise defined function, what you want to focus on to identify the discontinuities are first any restrictions of your separate pieces. Okay, so you should think about, are there restrictions on x squared minus 1? There are not. Are there restrictions on 4x minus 4? There are not. So good news, we don't have any points of discontinuity here or here. The second thing you need to do, and this is usually where you're going to find your point of discontinuity, if anywhere, is at your boundary point at the partition of the domain. And so if you're looking at this part, the boundary point is -1, x equals -1. And what you want to do is set up a limit as x approaches -1 from the left of h of x, and a limit as x approaches -1 from the right of h of x, and you will be using each of the parts, each of the pieces of the piecewise defined function to find those limits. So when x is less than -1, that means you are to the left of -1. So to find the limit as x approaches -1 from the left, you would be using this piece. And so you would be taking -1 squared minus 1. -1 squared is 1. 1 minus 1 is 0. And so that's the left-hand limit. For the right-hand limit, we would be using the part of the piecewise where x is greater than or equal to -1. Think whenever you're to the right of -1, you are at an x-coordinate that is greater than -1. So that would be this piece. So take -1 and sub it in to the 4x minus 4. 4 times -1 minus 4, that is not 0. Okay, be careful here. This is -4, and -4 minus 4 is -8. So what we see here is that there is a point of discontinuity for this h of x function at x equals -1. And can you tell what type it is? I think you should be able to tell what type it is based on what we've discussed so far. Just going back as a reminder, remember this? A jump discontinuity has a left-hand limit that exists, a right-hand limit that exists. However, the overall limit doesn't exist. And so that's what we're looking at here. We have a left-hand limit, we have a right-hand limit, but they don't match, which means the limit as x approaches -1 of h of x does not exist, and that means there is a jump. Discontinuity, I'm going to abbreviate. Jump discontinuity at x equals -1. All right, so that's just a couple of different examples of seeing the three main types of discontinuities that we will be looking at in AP Calculus: removable discontinuities, aka holes, jump discontinuities, or infinite discontinuities, aka vertical asymptotes. Not that you won't see oscillating, but we just don't specifically talk about them in the context of the definition of continuity. Okay, the next thing that I want to discuss with you are a couple of important theorems now that you know continuity. Before we, this is not in the notes packet that you have. However, I want us to, before we jump into properties and theorems, I want you to take a look at this question and these three functions. Are the following functions continuous? Y equals x. Y equals x squared. Y equals sine of x. I hope you're nodding your head yes for all three of those. Those are continuous functions. You know that they're continuous functions because, first of all, they're very common functions. They're, a part of the basic functions that you should learn before taking calculus. And so you should know that the domains are all real numbers. There are no restrictions on any of those functions. Okay, that's important to know that there are a lot of functions that you can say, I know the domain of this function, so I can easily say, because there are no restrictions in that domain, it is continuous. The function is continuous at all points. Next, in your notes, we have these properties of continuous functions. I'm not going to talk about these for very long, so if you are taking notes, you should pause the video to write them down in your notes packet. Okay, what this says is that if you have a function f that is continuous at a point and g is continuous at a point, then you can say that these combinations are also continuous. You can add two continuous functions and preserve continuity, subtract, multiply, You can take a constant times a continuous function and divide, provided that when you take that function g to the denominator, it does not equal 0 at whatever point in particular you're talking about. Also, our particular curriculum notes that there is a composite of continuous functions theorem that says that if you have a continuous function at x equals c and another continuous function at the function value of c, then the composite of those functions is continuous at x equals c. I'm not going to spend too much time talking about that. It's just out there, so I wanted you to note it. And then I have this note here at the bottom of the page that says that the properties that we just discussed in this composite of continuous functions theorem, it allows you to assume continuity for many different types of functions. Because you know that the properties preserve continuity. Basically, if you're looking at something like y equals the absolute value of x sine x divided by x squared minus 2, well, you can say that that is going to be continuous for all x values, for all x equals c's, especially because the denominator cannot equal 0, right? X squared plus 2, that can't equal 0 anywhere. And so that's just something that's important to keep in the back of your mind, that a lot of times you need to think about continuity and those properties, and that theorem help you do that. All right, next we're going to talk about a really important theorem. Now that we know continuity of a function, we can discuss the intermediate value theorem. And this is a moment where I need to tell you this. You are going to encounter in this course in AP Calculus AB 3 value theorems. There is the intermediate value theorem, there is the extreme value theorem, and then there is the mean value theorem. And so it's important to sort of keep track of them, note them, and what I want you to note in particular is that they are called existence theorems, meaning they guarantee the existence of values, and that's something important that we need to use as we proceed with our study of calculus. The intermediate value theorem is the first one because it's pretty simple. It is saying that if you have a continuous function over an interval, and you have a y-coordinate somewhere in between the y-coordinates of the endpoints. That's what k is a real number between f of a and f of b means. It means k is a y-coordinate somewhere in between the function values of the endpoints, or the y-coordinates of the endpoints. Okay, if you have that set of conditions, then there exists a number c in the open interval AB. So c is an x-coordinate because it's in between the x-coordinates of the endpoints. Then f of c equals k. Okay. I just paused for a minute because I just remembered that this is the place where we get to note the unfortunate letter choice used here. And I think the textbook does this on purpose. I noted that I looked this theorem up in the AP course description, and I noticed that instead of using the letter K, the only difference in the AP course description is they changed the K's to D's, which, makes a little bit less distracting for all of us, and it makes sense, A, B, C, D. However, I left the K just to, have a little chuckle at it. Do you see what I'm talking about here? Because eventually you're going to see it and you're going to be like, what? Okay, that's all I'm going to say. All right, anyway, what this theorem is saying, I'm just going to draw a little something on this graph. We have a continuous interval from A to B. And what this is saying is that the y-coordinate k, let's just put k like right here. It exists somewhere on this curve between A and B, and in particular, it's going to exist somewhere, I could put C like right here, somewhere where k would fit in between the y-coordinate of the left endpoint and the y-coordinate of the right endpoint. So let's just put it right there. Okay, so basically it just guarantees the existence of a y coordinate. That's what the intermediate value theorem does. Or I always, like, when you start to prepare for the AP exam, if you're doing that, you'll hear me talk about the existence theorems, and I will say things like the intermediate value theorem, or we call this IVT for short, just so you know. The intermediate value theorem guarantees the existence of just a function value. That's what it guarantees. Okay. So the first example, I forgot I had this in here. Have fun. All right. Before we talk about that, I do see students, when we start to talk about the value theorems, they just sort of go, it's not exciting. Why? Like, it's not that important. So I like to do a little bit of research on that stuff whenever I have time. And I love the math stack exchange because you can just sort of follow conversations and maybe learn something from it. So if you're interested in why the mean or intermediate value theorem is important, you can take a look at this math stack exchange conversation. I enjoyed reading it. I'm not going to read it right now to you, but I will put this link in the description of the video so you can access it if you would like to. It's a nice little conversation. All right. Anyway, let's look at a pretty simple example, and this is an AP example problem, multiple choice AP problem. It is really old, I know, 1997, but I just like it, so I left it there. Okay. So what we have here in the stem of the problem is it says let f be a continuous function on the closed interval from -3 to 6. If f of -3 equals -1 and f of 6 equals 3, then the intermediate value theorem guarantees that, and then you have to choose the correct answer. So it's asking you to think about the intermediate value theorem, and it's basically just testing you on, do you know the conclusion of the intermediate value theorem? Do you know what the intermediate value theorem is guaranteeing the existence of? Okay, so let's go through each of the options, and I'll talk about why certain options don't work. Like A. A doesn't work. Okay, here's why. We'll get a red pen to strike the ones that don't work. Okay, the intermediate value theorem guarantees the existence of some y-coordinate, but not a specific y-coordinate. So to say that f of 0 equals 0, that is so bold. You do not have enough information to say specifically an x-coordinate would have some sort of y-coordinate here. You don't have enough information about f to say that, and so that one is out. B is definitely out because you have not even seen this notation yet. This is derivative notation, which you'll see in the next unit. We are not talking about derivatives yet, so that is definitely out as an option. That's actually looking at the mean value theorem. Okay, but we're not there yet. All right, let's take a look at C. -1 is less than or equal to f of x is less than or equal to 3 for all x between -3 and 6. This one is tempting, however, you need to be careful. The intermediate value theorem is not saying that all of your y-coordinates are between the y-coordinates of the y-coordinates of the endpoints. Okay, look at this. The y-coordinate at whatever x value this is, it goes below this y-coordinate. Okay, and that can happen. The intermediate value theorem is not saying that all of your y-coordinates have to be in between certain values. So that's why we're going to strike that one. Okay. And so that leaves us with D or E, and they look very similar. And actually, if you only focus on this part, f of c equals 1, f of c equals 0, both of those could work because 1 is in between -1 and 3, which are my y-coordinates, and 0 is in between -1 and 3. So again, either one of those could work. So what you need to focus here is on the other part where it says for at least one c between -3 and 6, or for at least one c between -1 and 3. Well, what I want you to keep in mind is that c is the x-coordinate. So c needs to fall between the x-coordinates of the endpoints, not the y-coordinates. What are the x-coordinates of the endpoints? Right here. -3 and 6. Right here. Okay, and so that is why D is our correct answer. E is not. These are the y coordinates. Okay, yes, we need the y value falling in between -1 and 3. It does. But the C value falls in between -3 and 6. Okay, so again, that's just sort of showing fully, what is the intermediate value theorem. This is the hypotheses of the intermediate value theorem. This would be a conclusion. All right, now let's do a little bit of a more fun example here. Example 4. Is any real number exactly 1 less than its cube? Okay, so nowhere in this question does it ask you to use intermediate value theorem, but this is a good type of question where you can invoke the intermediate value theorem. And here's how. The question is any real number exactly 1 less than its cube. You could turn that into an equation. Is any real number, let's just grab a different color. Okay. Is any real number, let's call it x, any real number, is any real number exactly equal to 1 less than its cube? Take 1 less than its cube and turn that into an expression for the second part of this equation. Okay, 1 less than its cube. Its cube minus 1 is an expression that could be used for 1 less than its cube. And so what we have here now is an equation that basically we're just now asking ourselves, can this be solved? So we took the initial question and we turned it into, we reworded it into another question that is asking the same thing. Can x equals x cubed minus 1 be solved? Well, I'm going to rearrange this equation a little bit. I'm going to put it in standard form. We could write that as x cubed minus x minus 1. So I'm subtracting the x. And if I'm subtracting the x, that means I have a 0 on the other side. Now we're asking, can this be solved? And again, that's all still asking the same initial question, just in a little bit of a different way. And if you're asking whether either this equation or this equation can be solved, but I like this one a whole lot better because you have a value here, you can use the intermediate value theorem to determine if that equation can be solved. And so that's a nice practical application of IVT, is that you can use IVT to determine if an equation can be solved. Now, before we do that, I just want you to know we're not actually going to solve the equation here. The question wasn't what is the real number. It's just asking, is there one that exists out there? Is that something that is, real? And so we're not going to solve this equation. We are just going to state whether it can or can't be solved. And again, IVT can do that for us. So what I'm going to do here is I'm going to set up, I'm going to say consider a function. I'm going to set up a function with x squared x minus 1. Okay. So what I'm looking for here is there a value for x such that when you sub that value in for the x's here, you get 0? Okay. Is there a c? Does a c exist such that f of c equals 0? Okay, so we just reworded the question one more time, and if we can answer that question, we can answer our initial question. Okay, it's asking the same thing. And so this is where typically if I was in class with you in person, I would say, just give me a number. Give me a number that maybe would work as a C value, that when you throw it in for X, it works. Sometimes I have students say 0. Sometimes I have students say, no, 0 is not going to work. How about 1? I don't know. So I'm just going to pick an X coordinate to try like 1. Okay, I usually tell my students, try something simple. f of 1. So we just picked an x-coordinate, f of 1, and it does not get us 0. If you think about it, 1 cubed minus 1 is 0, but then minus 1 again is negative 1. Okay, but it actually does something useful for us. It gets us a value that is less than 0. And so that's a good starting point. Okay, we got a value that's lower than the value that we're trying to get. And so then what I tell my students is we're actually in a good place right now. Let's come up with another x-coordinate and find its value. And what we actually, I don't even care if we get 0. We're not going to. Not that it doesn't exist, but I say keep with simple numbers. So let's come up with a number that you could put in for x, like 2. That'll give us something bigger than 0. So 2 cubed minus 2 minus 1, what's that? All right, so that's 8 minus 2 minus 1. What's to get us there? 5. Okay. And so what we now have found is that we have this interval. We have an x-coordinate from 1 to an x-coordinate of 2. And f of 1 is equal to negative 1, and f of 2 is equal to 5. Okay, 0 falls in here, right? 0 is somewhere in there. Finally, our function, x cubed minus x minus 1, is it continuous on this interval from 1 to 2? Yes, it is continuous everywhere, right? This x cubed minus x minus 1 has no restrictions. So we can say f of x is continuous on the interval from 1, 2. And since it is continuous and we found an interval where we have a number that is lower than the value we're looking for, a number that's higher than the value that we're looking for, we can say yes, f of c equal to 0 does exist. It exists. And that is by, I'm going to leave a little bit of room here, by IVT. And since the answer to this question is yes, that means the answer to these questions is yes, and that means the answer to your question is yes. Again, by the intermediate value theorem. So if you're ever faced with an equation and you are trying to determine whether the equation can or cannot be solved, you can most likely use intermediate value theorem to determine that. Now keep in mind, it all hinges on the fact that you have a continuous function over an interval. So that's really important. We're talking about continuity here. If you end up with a discontinuity, then you cannot use the intermediate value theorem. Okay, finally, the last example sort of pulls it all back together, and we go back to that simple looking graph to sort of, go over again what we've discussed in this section. Okay, but I'm going to simplify the first parts just to make it go quickly. We're using this graph, and let's call it f of x again. And y equals f of x. We are asked first identify where the function is continuous. I'm actually not going to do that first. I'll do that second. Part B is identify points of discontinuity. I'm going to do that first. And then part C, prove that there exists a C in the domain of f such that f of C equals 1.5. Okay, we'll finish up with that. Let's do part B first. It's so easy. We already did this at the beginning of this notes section. Where's the points of discontinuity? They are at x equals 1 and x equals 2, right? And I'm not going to say much more about that because we already sort of beat that to death at the beginning. We did the limits, we did the function values, we did all of that. We know that those are points of discontinuity. Now I did that part first because we already did that at the beginning, but also it helps us to easily identify where the function is continuous. It's continuous everywhere else on the interval from 0 to 4, right? And so we're just going to use interval notation to identify where the function is continuous. It is continuous at starting at x equals 0 because that's the left endpoint, to x equals 1. However, it's not continuous at x equals 1, so put a parenthesis there, closing that part off. Let's union that with another interval, picking back up with 1. Continuous everywhere until x equals 2. not continuous at x equals 2, so you need parentheses around the 2's. And finally, it is continuous everywhere from 2 to the end point of 4. So let's end with our 4 there, bracket around 4. Okay, little review of interval notation to show here where the function is continuous. Finally, part C, prove that there exists a C in the domain of f such that f of c equals 1.5. The most important thing I want you to get out of what you're looking at there in that set of directions is that you are thinking about the intermediate value theorem to do that. Here's 2 reasons why. First of all, it's asking you to prove the existence of something. And in particular, it's giving you a function value to prove exists. Prove that there exists an x for this function value, for this f of x. That is definitely IVT. Okay, like I said, you're going to learn 2 other value theorems in AP Calculus, and you need to know, that they are existence theorems, and you need to know that intermediate value theorem, that's the first one, is guaranteeing the existence of a function value. Okay, so how are we going to do that? Well, we're going to go back first of all, and we're going to look at the intermediate value theorem. It says that the function is continuous over some interval, and the function value, okay, look at where the k was. It says k, but let's look down here in the conclusion. The function value is between the y-coordinates of the endpoints. So here's what I did. I said that the proof is trivial, and I stopped. No, just joking. All right, here's what I did. I looked for a place where I could easily say that my function was continuous over an interval. Okay, a nice interval where my function, up here, we're looking at this function, is continuous, and where 1.5 would fit between the endpoints, where the y-coordinate of 1.5 would fit between the endpoints. And so again, you want to stay away from discontinuities, so you want to kind of stay away from x equals 1 and x equals 2. Take a look at this little section though, x equals 3 to x equals 4, okay, on that interval, on the interval from 3 to 4, we could say that f of x is continuous, right? No discontinuities there, so that's really great. The second part, again, of the intermediate value theorem says that the value that you're looking for, this would be our k, it has to be between f of a and f of b. Now it's just on a decrease here, a decreasing section, so that means it's like the f of 4, the f of b is the lower y-coordinate, that's 1, and f of 3, which is the higher y-coordinate, is 2, and 1.5 fits right in here, right? And so since we have established that the conditions of intermediate value theorem work, they apply, we can say therefore there exists a C in the interval from 3 to 4 such that f of c equals 1.5 by the intermediate value theorem. Yay! All right, I really like that example too. I think it's fun. As usual, I really hope this was helpful, and reach out, contact me if you have any questions. Bye.